In this equilibrium problem, we have a bridge 24 meters long and weighing 500,000 newtons, supported by two pillars located at each end. The 20,000 newton car is parked 6 meters from one end of the bridge. How much force does each pillar exert? So we'll draw our free body diagram. Here is our bridge and our two pillars, one on each end. And we know that the total length of the bridge is 24 meters. We also know that there is a car 6 meters from one end. Then we want to draw our forces. We know that the gravitational force of the car is going to be 20,000 newtons. So I'll write down here my givens. And we also know the gravitational force of the bridge itself is 500,000 newtons. Now, when you have the gravitational force of an object, it's a very long object where you draw it. You always draw it in the center. So the gravitational force of the bridge is 500,000 newtons. Technically, it's a center of mass, but since it's a uniform bridge, we can consider that to be the exact center of the bridge. Then we have the two forces of the pillars. Now, this pillar, because the car is closest to it, will have to exert a much larger force than the other pillar. And think of it this way, is if you are helping somebody move a table, and there's a lot of stuff piled on your end, you'll have to exert a much larger force to carry the table. So we are in equilibrium because nothing is moving. And so we have that the total torque is equal to 0, where torque is Fd sine of theta. Now the issue in this case is that there is no clear-cut fulcrum. So where do you place a fulcrum if you don't have a clear-cut one present available? And here's the key. If you have more than one force, if there's more than one force, you place the fulcrum at one of those unknown forces. So if there are more than one unknown force, then put the fulcrum at one of the unknown forces. What this will do is it will make the torque from that force 0, because the distance is 0. It would be like trying to open a door by pressing at the hinge. You can't turn the door if you press at the hinge. So there's as many torques as there are forces that are not at the fulcrum. So there are 3 forces not at the fulcrum, and so there are 3 torques. There's a torque from the car, the torque from the bridge, and the torque from the second pillar. And those add up to 0. Now the car and the bridge will make this pillar rotate clockwise, so they are negative. And the second pillar would make it rotate counterclockwise, so that is positive. And so now we replace each one with Fd sine of theta. So we have the opposite of the force of the car, 20,000, times its distance, it is 6 meters from the fulcrum, times the sine of 90. That angle is going to be 90 degrees, as all of them in this case will be 90 degrees. They will all be 90 degrees in this case. And the sine of 90 is 1. So I'm going to abbreviate this because I'll run out of room. I'll just say times 1. Minus 500,000 times the distance. Now that bridge we wrote halfway across the bridge, 12 meters. Times the sine of 90, which is 1, plus force 2, times the distance, 24 meters, times the sine of 90, which is 1, is equal to 0. And so we got the force from the second pillar to be 255,000 newtons. But it also asks for the force from the first pillar, which we expect to be more. Now in this case, we are also in translational equilibrium, which means all of the forces add up to 0 as well. Now those forces are in the y direction, and there's 4 of them. Whether it's located at the fulcrum or not, they exert force. The two pillars are up, so they are positive, and the car and the gravitational force of the bridge are down, so they are negative. So we have force 1 plus 255,000 newtons minus 20,000 newtons minus 500,000 newtons is equal to 0. And so we get the force from the first pillar to be 265,000, which is more than the force from the second pillar, which is what we expected. So we should feel comfortable with our answer.